Hello, and welcome to the ACGIH e-learning program and today's webinar, ACGIH Velocity Pressure Calculation Method, Making It Easy. My name is Phil, and I'll be the moderator today. The handout for today's webinar is available on our online learning management system, ACGIH Academy, which is accessed at learning.acgih.org in the handout tab of the course, or click on the handouts in the GoToWebinar control panel to make a printable copy. Earn all your education contact hours conveniently with ACGIH's 2022 Learning Pass. With 24 webinars on topics such as wearable devices, respirator fit testing, and pandemic facility risk assessment, providing over 30 education contact hours, the Learning Pass offers you the flexibility to participate at an affordable rate. Visit our website for more information. And announcing the new Bioaerosols Agent Introductory Lecture Series. Come join us for an 8-week virtual course every Tuesday at noon Eastern, beginning October 11th, 2022. Each lecture features a deep dive presentation by an industry expert on specific types of bioaerosols, such as bacteria, fungi, viruses, and endotoxins. Visit our website for more information. Save on ACGIH's newest publications. Explore our upcoming book releases and pre-order yours today. Don't miss out on the chance to expand your OEHS library at a discounted rate. Visit the ACGIH publication store today. Get top quality education virtually with the Basics in Industrial Ventilation online course. Earn a total of 9.25 education contact hours with this online professional development course taught by industrial ventilation experts. This virtual course includes recorded sessions, handouts, and comprehensive testing, perfect for a professional looking to expand their career knowledge into industrial ventilation. More information can be found on our website. And don't miss out on a chance to attend the popular Fundamentals of Industrial Ventilation course. Join us in Chicago on October 17th. This hands-on course taught by world-renowned industrial ventilation experts covers both basics and advanced topics related to industrial ventilation and related calculations. More information can be found on our website. And new this year, we're offering an advanced industrial ventilation course. Join us in Las Vegas, October 24th through the 27th for this next level instruction course that will provide education on advanced topics taught by the world's leading industrial ventilation experts. And announcing a new subscriber benefit, ACGIH's Data Hub. Get access to nearly 800 TLV and BEIs along with the supporting scientific documentation in a mobile-friendly format. Available complimentary to subscribers. Enroll today and get benefits valuable to your career. ACGIH offers many opportunities to advance the careers of OEHS professionals. ACGIH offers many benefits, including complimentary ones valuable to your career growth, which includes an annual TLV BEIs book, Data Hub access to all of the TLV and BEIs with scientific documentation. The Action Level, which is our at-home self-studying continuing education program, and online monthly issues of the Journal of Occupational and Environmental Hygiene. The 2022 TLV BEI book and the 2022 Guide to Occupational Exposure Values are now available in both print and digital format. Also available now is Air Sampling Technologies Principles and Applications. This new much anticipated book covers the practical application of modern sampling devices. Information on the utilization of the sampling results is found within this up-to-date resource containing industry expert methodologies. Visit the ACGIH publication store today. And now for some housekeeping and tips. In order to obtain a certificate of completion, the test and satisfaction survey must first be completed in our online learning management system, which can be accessed at learning.acgih.org. Once completed, your certificate will become available to download and print. All attendee computer lines are in listen-only mode. Audio streaming quality is determined by your computer's connection. If you are unable to hear or see the webinar, a recorded version will be available after the broadcast. It may take up to 48 hours before the recording is available. To submit questions, send an email to science@acgih.org. Today's webinar will be 1.5 hours in length and may be eligible for CM and recertification points. Please check with the individual organization as to the availability of this credit. Please note this webinar and all ACGIH webinar materials are fully protected by the United States copyright laws. With that, today's presenter is Dale Price. Dale is president and owner of M&P Air Components, a manufacturing representative company for industrial fans in Southern California. Dale has over 40 years of experience in the design, application, and sales of dust collectors and industrial fans. Dale also has over 30 years of tenure with the Alabama and Las Vegas Industrial Ventilation Conferences. As an instructor at the Michigan Industrial Ventilation Conference and chair of the West Coast Industrial Ventilation Conference, Dale is a member of the ACGIH Industrial Ventilation Committee. With that, Dale, I hand it off to you, sir.
Thank you, Phil, and welcome this morning. Thank you for joining us on the ACGIH e-learning program. As Phil said, today's webinar is going to be the ACGIH velocity pressure calculation method, and let's make it easy. Again, I'm out of Huntington Beach, California. I have 38 plus years experience in design and application of dust collectors and industrial fans. I have over 30 years of tenure with the Michigan, Alabama, and Las Vegas Industrial Ventilation Conferences. I'm also the director of the West Coast Industrial Ventilation Conference and a member of the ACGIH Industrial Ventilation Committee. Introduction. The ACGIH velocity pressure method is a consistent, accurate, and reliable method for calculating static pressure losses in an industrial ventilation system. This method is repeatable, it's versatile, and once calculated for a given condition, losses for other conditions are easily and accurately determined. Now, this presentation introduces the velocity pressure method for calculating static losses, while Chapter 9 of the Industrial Ventilation Manual gives detailed, step-by-step instructions for calculating all static pressure losses for local exhaust ventilation systems, which we call LEV systems. The ACGIH velocity pressure method calculation spreadsheet is recommended for calculating static pressure losses for both simple and complex LEV systems. In this presentation, we'll be using the ACGIH velocity pressure calculation spreadsheet in some examples. However, guidelines on how that spreadsheet is actually used will be covered in a separate ACGIH webinar. We're going to talk about the basis of use. We're going to talk about loss factors, how the system works, and then a brief summary. Basis of use. First, velocity pressure. Velocity pressure, which we term VP, is the kinetic energy of an airstream which moves the air from rest to its actual velocity within the system. Now, velocity pressure only acts in the direction of flow. It's always a positive value, and we measure it in inches of water gauge. Velocity pressure is calculated with this formula, which says velocity pressure is equal to the airstream velocity divided by a constant, which is 4,005. You square that value and multiply it times the density factor, where velocity is always in feet per minute. The density factor is a ratio of the actual airstream density to standard airstream density, with standard airstream density being considered as 0.075 pounds per cubic foot. Now, this means that for any given velocity, then the velocity pressure is going to vary with the change in airstream density. For instance, if we have a 30-mile-per-hour wind on both a 10-degree day and a 100-degree day, the pressure generated by that 30-mile-per-hour wind will be heavier, greater on the 10-degree day because the air is colder and more dense than on the 100-degree day. So velocity pressure for any given velocity will always vary with the change in airstream density. Within a system, velocity pressure is recognized as the system total pressure minus the system static pressure, where each of these values are also in inches of water gauge. Static pressure. Static pressure, which we call SP, is a pressure required to overcome resistance to flow due to duct friction, dynamic, turbulence losses, mechanical losses, and all other system losses. Now, static pressure acts in all directions regardless of flow. It can either be negative or positive, and we measure it perpendicular direction of flow. And we also count it also in inches of water gauge as well. Within a system, static pressure is recognized as the system total pressure minus the velocity pressure. Again, everything is in units of inches of water gauge. Conservation of energy. The law of conservation of energy states, first, energy cannot be created or destroyed as it moves through a system. That's the first law of thermodynamics. Second, the total energy in an airstream is measured by its total pressure, and it's constantly decreasing in the direction of flow due to frictional and dynamic losses. Energy forms within a system, such as velocity and static pressure, can be converted from one to another. And the law of conservation of energy is fundamental to calculating pressure losses in an industrial ventilation system. Along with the law of conservation of energy is Bernoulli's equation. From the law of conservation of energy, Bernoulli's equation is applied to a frictionless ideal fluid with a constant mass and states that the velocity and static pressure energies are mutually convertible. This means that velocity pressure can be converted into static pressure, and static pressure can be converted into velocity pressure. So, at any point in a system, VP1 plus SP1 will always equal VP2 plus SP2. And intuitively, we can see this because we know that at any point in a system, if our static pressure decreases, we will see an increase in flow. And the reason we see the increase in flow is with this decrease in static pressure, that decrease in static is converted to an increase in velocity pressure. As that velocity pressure increases, our velocity increases. And since flow is area times velocity, then flow then increases. We can also see it because we know that if at any point in the system our static pressure increases, our flow rate decreases. And the reason for that is that increase in static pressure comes from a decrease in velocity pressure. And as our velocity pressure is diminished, our velocity decreases and therefore our flow rate decreases. So this forms a basis of use of the velocity pressure method for calculating frictional and dynamic static pressure losses. We can then account for frictional and dynamic pressure losses in terms of static pressure by applying what we call loss factors to the airstream velocity pressure at any point in a system, so that static pressure is equal to F sub x times our velocity pressure, where F sub x is a system component loss factor unique to each system component. So let's look at some of the loss factors. First, for duct friction. Duct friction loss is calculated by multiplying a duct friction loss factor, which we call F sub D, by the duct velocity pressure, which we call VPD. So to determine our duct loss, we simply multiply our duct friction loss factor, F sub D, times velocity pressure for our duct, VPD. F sub D is our loss factor, and all of our loss factors are dimensionless. Our velocity pressure is our duct velocity pressure, and that is in inches of water gauge. So how do we determine F sub D? Well, F sub D is further determined by F prime sub D times L, where F prime sub D is a duct friction loss factor per foot of duct. L is the length of duct. So F sub D is then F prime sub D times L. F sub prime sub D is determined for metal or plastic duct by the formula 0.0307 times our velocity raised to the 0.533 power divided by our flow rate raised to the 0.612 power, where our velocity is always our duct velocity in feet per minute, and Q is our flow rate, also in cubic feet per minute. Now, I'll note that when we talk about plastic duct here, we're talking about hard plastic duct, not flexible. So when we say plastic duct, we're talking about fiberglass or PVC ducting. And for those of you who prefer to use tables and charts instead of formulas, you can also determine F prime sub D from Chapter 9 of the Industrial Ventilation Manual, figures 9B and 9C, which gives F prime sub D in a chart form based upon flow rate, duct diameter, and velocity. And then if you need to determine what F prime sub D is for flexible duct, there's also a formula 9.6 in Chapter 9 that F prime sub D can be calculated for flexible duct. Let's look at an example. We have a duct segment. Our length is 100 feet. Our duct flow rate is 3,300 CFM. Our duct diameter is 12 inches. Our duct velocity is 4,200 feet per minute. And our duct velocity pressure is 1.1 inches of water gauge. How do we calculate our duct loss? Well, first, we need to determine our F prime sub D and use in our calculation of 0.0307 times our duct velocity raised to the 0.533 power divided by our flow rate raised to the 0.612 power. We can determine that our F prime sub D is 0.0184 per foot of duct. And again, you can also gather that number from the tables in figures 9B and 9C in the ventilation manual. So now that we know F prime sub D, we can determine F sub D. F sub D is simply our friction loss factor per foot of duct times our duct length, which is 0.0184. In this case, we have 100 feet of duct. And so F sub D is 1.84 for this particular example. Our duct segment loss then is our F sub D times our duct velocity pressure, which is 1.84. And we said our duct velocity pressure is 1.1 inches of water gauge. So our duct segment loss is 2.02 inches of water gauge for 100 feet of duct at 3,300 CFM at 4,200 feet per minute. Now, what if we change the duct length to 50 feet? If we change the duct length to 50 feet, our F prime sub D remains unchanged, but our F sub D calculation changes to our length of being 50 feet instead of 100 feet. So F sub D becomes 0.92, and then our duct segment loss becomes 1.01 inches of water gauge. Let's look at an example on an elbow. The dynamic pressure loss incurred in an elbow is calculated by multiplying the elbow loss factor, which we call F sub L, by the duct velocity pressure, VPD. So our elbow loss is our elbow loss factor, F sub L, times our duct velocity pressure. And also note, elbow loss factors are for elbows having what we call zero length. The elbow friction loss is accounted for in the duct friction loss calculation. And let me illustrate that. Here, where's my pen? There we go. If we come across the center line of this elbow in this direction and the center line of our elbow in this direction, then when we measure our duct length, we're going to measure our duct length all the way to the center line of the elbow here. And we're going to measure our duct length all the way to the center line here. This allows all of our friction losses within our elbow to be accounted for in our duct friction loss calculation. And from that, the losses in our elbow loss are these dynamic losses that occur as the air moves through the elbow itself. Let me get out of here, go here, erase this. So let's look at an example. We have a 90-degree 5-piece elbow with a 2 centerline radius. We have a flow rate of 3,300 CFM, 12-inch duct diameter, 4,200 feet per minute, duct velocity, and our duct velocity pressure of 1.1 inches of water gauge. In Chapter 9 of the Industrial Ventilation Manual, we have a table that gives us our elbow loss factors for various elbow configurations and centerline radiuses. And here in the left column, we have a stamped elbow, a 5-piece, 4-piece, and 3-piece elbow. Across the horizontal, we have a centerline radius of anywhere from 0.75 to 2.5. For our example, we have a 90-degree 5-piece elbow. That's this guy right here. 2 centerline radius. That's this guy right here. So our F sub L for a 5-piece 2 centerline radius is 0.19. Knowing that, we can calculate our elbow loss, and our elbow loss is our F sub L, which is 0.19, times our duct velocity pressure, which is 1.1, and that value is 0.21 inches of water gauge. Now, what if we change the elbows to a 1.5 centerline radius? If we change our elbow to 1.5 centerline radius, we still have our 5-piece elbow. This 0.19 factor changes to a 0.24, and we use a 0.24 in this calculation, and our elbow loss is recalculated based on a 2.4 times a 1.1. Very simple, very easy process. Look at an example on a branch entry. The dynamic pressure loss incurred in a branch entering a duct is calculated by multiplying the branch entry loss factor, which we call F sub n, En, by the branch duct velocity pressure, VPD. So our branch entry loss is our entry loss factor for our branch entering the main times our duct velocity pressure. Let's look at an example on this. If we have a branch entry angle of 30 degrees, flow rate of 3,300, diameter of 12 inches, duct velocity 4,200 feet per minute, duct velocity pressure of 1.1 inches of water gauge. Again, in Chapter 9 of our ventilation manual, we have a table that gives us our entry loss factors based upon the angle of entry of the branch into the main. We said that our entry angle is 30 degrees. So for a 30-degree entry, our loss factor is 0.18. Now, note that we only calculate our losses in the branch and not in the main. And we're not going to include a regain calculation, even though you think, well, we have 2 smaller ducts going into a larger duct. What about a regain? Well, we're not going to calculate a regain because in some cases that actually becomes a loss and not a regain. And we'll deal with that in a later part of this webinar. So when we're calculating our entry loss, we're just calculating the dynamic loss of these 2 air streams merging into a main duct. So then our branch entry loss is our entry loss factor, F sub n, times our duct velocity pressure. And we said for a 30-degree angle, this is 0.18. So 0.18 times our velocity pressure is 0.2 inches of water gauge. Now, what if we change our branch entry to 45 degrees? If we do that, then going to 45 degrees, this loss factor of 0.18 for a 30-degree entry goes to a 0.28 for a 45-degree entry, and this value changes accordingly. Let's look at a hood example. Both dynamic and acceleration losses are accounted for in calculating the hood static pressure, which we call SPH. For a simple hood, these losses include first, the hood entry loss, which we call F sub H, and that's a turbulence loss based on the hood geometry and its effect on transitioning the airstream into the duct. Then we have a second loss, which is acceleration loss, F sub A, which is the energy required to accelerate the airstream from rest outside the hood all the way up through the hood into the duct velocity. Unlike the other loss factors, which vary based upon the type of elbow, the shape of the hood, the length of duct, F sub A is always 1.0. Now, both the hood entry loss and the acceleration loss are calculated by multiplying their loss factors by the duct velocity pressure. So here we have our hood static pressure is our F sub H, which is a hood entry loss based upon the hood geometry, times our duct velocity pressure, plus F sub A, which is always 1.0, which is acceleration loss, times our duct velocity pressure. Let's look at an example on a hood calculation. We have a simple hood. It's rectangular. It has our taper angle, this guy right here, of 45 degrees. Same flow rate, 3,300, duct diameter 12 inches, duct velocity 4,200 feet per minute, duct velocity pressure 1.1 inches of water gauge. Again, in Chapter 9 of the ventilation manual, we have a table that gives us our F sub H, or hood loss factor, based upon the taper angle and whether it is a round or a rectangular hood. In our case, we have a taper angle of 45 degrees. We have a rectangular hood, so our F sub H is 0.25. Knowing that, we can calculate our hood static pressure, which is our F sub H, 0.25, times our duct velocity pressure, which is 1.1, plus our acceleration loss, which is our F sub A, which is always 1, times our duct velocity pressure, which is 1.1, and that calculation gives us a hood static pressure of 1.38 inches of water gauge. Now, what if we change the hood taper angle to 60 degrees? If we change this hood taper angle from 45 to 60, then our F sub H changes from a 0.25 for a 45-degree taper to a 0.16 for a 60-degree taper. This value changes, and our hood static pressure changes accordingly. Now, other loss factors. Additional loss factors are listed in Chapter 6, which is hoods, Chapter 7, which is fans, Chapter 9, which is systems, and Chapter 13, which are specific operations of the Industrial Ventilation Manual. They include SEF, which is fan system effect factors, and these would be found in Chapter 7. F sub S, which is a entry loss factor for a slot, that would be found in Chapter 6, Chapters 9, and Chapter 13. And in case where you have a slot, that would be considered a compound hood, so you would have your F sub S entry loss across a slot. You would still have your F sub H entry loss, which is from the hood into the duct, and then of course your acceleration loss. And then Chapter 9, F sub EXP for expansion or regain fittings. Also in Chapter 9, there's figure 9G for weather cap. And I bring this up because we do not recommend the use of weather caps in either system design or redesign. However, we do recognize that there are a lot of systems out there that have weather caps installed. And so we do list loss factors for weather caps in figure 9G of Chapter 9 so that you can use that data to evaluate the losses of an existing system. And then other loss factors are in Chapter 13 for specific designs. How it works. When the system design is changed, the new static pressure, SP2, is proportional to the change in the sum of the loss factors, the change in velocity pressure, and airstream density. So SP2 is equal to the sum of the loss factors for case 2 divided by the sum of the loss factors for case 1 times the velocity pressure for case 2 divided by the velocity pressure for case 1 times any change in density factors times our original static pressure for case 1. And this is really pretty simple. Now, when the system design is fixed, but the velocity changes, the new SP2 is proportional to the change in velocity pressure. The reason for that is, in this case, the system design is fixed, so the sum of the loss factors for case 2 equals the sum of the loss factors for case 1. So this drops out. That's simply a 1. It drops out, and SP2 is simply the ratio of the change in velocity pressure times the change in density factor times our original static pressure. When the system design is changed, but the velocity is held constant, the new SP2 is simply the ratio of the change in loss factors times any change in density factors times SP1, because again, at that point, if the velocity pressure is unchanged, this goes to 1. It simply drops out of the formula. Now, the velocity pressure method only applies to system frictional and dynamic losses which have an identifiable loss factor. Other losses, such as mechanical losses from dust collectors, heat exchangers, and things like that, must be added separately. Let's look at some examples on how this works. Here we have a simple design. Our flow rate is identified as 3,300 CFM. Our density factor is 1.0. We have one hood. It's a simple hood, rectangular, 45-degree taper. We have a 12-inch diameter duct. It's metal. We have 100 foot of duct length. We have one elbow. It's 90-degree elbow, 2 centerline radius, 5-piece. And we have one 30-degree branch entry. So let's look at what our loss factors are in this case. And our loss factors, first of all, F sub A we said is always 1.0. F sub H for this particular hood, over here in our calculation sheet, we find that F sub H we've entered is 0.25. So this guy is 0.25. F sub D, we find that on our calculation sheet of being 1.84. That's this guy right here. F sub L, which is our elbow loss factor for our elbow, is 0.19. It's this guy right here. F sub N, which is our entry loss, is this guy right here. It's 0.18. So if we sum F sub A is 1 plus 0.25 plus 1.84 plus 0.19 plus 0.18, we get 3.46. If we take the sum of our loss factors of 3.46, multiply it times our duct velocity pressure of 1.1, we'll get a segment loss of 3.81 inches of static pressure. Now let's look at how this works out on the calculation sheet. On the calculation sheet, it's basically broken down into 4 sections. You have a section for system data, you have a section for hood losses, you have a section for duct segment losses, and you have a section here for other miscellaneous losses. So let's look at it. In our duct section, we have a flow rate of 3,300 CFM. We have a 12-inch diameter duct. That gives us a duct velocity of 4,202 feet per minute and a duct velocity pressure of 1.1 inches of water gauge. In our hood section, we have an F sub H for our hood of 0.25. We said earlier that our hood entry loss is our F sub H loss factor times our duct velocity pressure, and that gives us a hood loss of 0.3 inches of water gauge. We also said that our acceleration loss was F sub A, which is 1, times our duct velocity pressure. So our acceleration loss is 1 VP, and that's 1.1. So our hood static pressure loss is our hood entry loss 0.3 plus our acceleration loss of 1.1, which is 1.4. And that's this value right here. And we also said in our duct section, we had 100 feet of straight duct. So this is our L. When we calculate our F prime sub D, we find F prime sub D is 0.018. And we said that our F sub D is our F prime sub D times our duct length, and that becomes 1.84. We said for a 90-degree elbow, 2 centerline radius, 5-piece, our F sub L was 0.19. That's this guy right here. And for a 30-degree branch entry, our F sub N is 0.18. So in our duct section, if we have 1.84 loss factor for our duct, plus a 0.18 loss factor for our branch, plus a 0.19 loss factor for our elbow, the cumulative loss factors in our duct segment is 2.21. And if we multiply that times our duct velocity pressure, that gives us a duct segment loss of 2.4 inches of water gauge. So then combining that with our hood loss of 1.4 inches of water gauge, that gives us a duct segment loss of 3.81 inches of water gauge. And again, you can see on our loss factors, the cumulative loss factors are F sub D, F sub L, F sub N is 2.21. We add our 1 for our F sub A, that's 3.21, plus our 0.25, which is this guy right here, and that sums up to our 3.46. Let's look at another example, and now we're going to change our flow rate. And let's see what happens when I change our flow rate. And what we're going to do here is we're going to take the same system, and we're going to change our flow rate from 3,300 CFM to 3,630 CFM. Everything else stays the same, except that does mean that our duct velocity increases from 4,202 to 4,622 feet per minute. And our duct velocity pressure also then increases from 1.1 inches of water gauge to 1.33 inches of water gauge. So then we can easily calculate SP2 by saying SP2 is VP2, which is 1.33, divided by VP1, which is 1.1. There's no change in our density factor, so that's a 1, times our SP1, which is 3.81, and that's 4.6 inches of water gauge. And again, let's look at how that works out on the calculation sheet. On the calculation sheet, our F sub H has stayed the same. Our F sub A is always 1. So our F sub H times our VPD, our hood entry loss still stays at 0.3. Our acceleration loss increases because 1 times our velocity pressure gives us 1.33 instead of 1.1. So that gives us a hood static pressure loss of 1.7, where before it was 1.4. In our duct section, again, our duct length stayed the same, our F sub D stayed the same, our F sub L stayed the same, F sub N stayed the same. So our total duct component loss factor stayed the same, 2.21 and 2.20. However, we're going to multiply those factors times different velocity pressure, which is now 1.33. And when we do that, we find that our duct loss increases from 2.4 to 2.9 inches of water gauge. That, summed with our hood loss of 1.7, gives us a cumulative loss of 4.9 inches or 4.59 inches of water gauge. So again, in this case, where our velocity pressure is the only thing that's changed, our increase in static pressure is simply the ratio of our velocity pressures. Let's look and see what happens now when we change fittings. We change our duct fittings. Now everything in our system data stays the same. Our flow rate's the same. Our velocity is the same. Our duct velocity pressure stays the same. But what happens to our energy loss factors? Well, F sub A is always 1. F sub H, in this case, we did not make a change to our hood, so that stays 0.25. F sub D, what happens to F sub D? Well, we've changed our ducting from 100 feet of duct to 150 feet of duct. And while that does not change our F prime sub D, it does change F sub D. And F sub D then changes from 1.84 to 2.76. So this guy now becomes 2.76. F sub L, we didn't change our elbow, but we did change the quantity of elbows. So while each elbow has an F sub N of 0.19, since we now have two elbows, the cumulative for our elbows is now 0.38. So this guy goes to 0.38. F sub N stays the same. We only have one branch entry. So our loss factors is an F sub A, which is 1.0, plus 0.25, plus our F sub D, which is 2.76, plus our F sub L, which is two elbows at 0.38, plus F sub N, which is 0.18, and that value sums to 4.57. So again, since our velocity pressure has stayed the same, SP2 is simply the change in our loss factors times SP1, 4.57 divided by 3.46 times 3.81 gives us an SP2 of 5.03 inches of water gauge. And again, let's look at how this works out on the calculation sheet. On the calculation sheet, again, we see nothing in our hood has changed. Our velocity pressure has not changed. So our hood static pressure has remained unchanged at 1.4 inches of water gauge. We said earlier that our duct friction loss factor has changed from 1.84 to 2.76. Our elbow loss factor has changed from 0.19 to 0.38. Our branch entry is still a 0.18. So now our cumulative loss factors in our duct has changed from 2.21 to 3.32. When we multiply that times our duct velocity pressure, we find that our duct loss has increased from 2.4 to 3.7. That combined with the hood loss of 1.4 gives us a 5.03 segment loss for our duct. And again, there's a little bit of rounding in the calc sheet, and that's why the 3.7 plus 1.4 shows up as a 5.03. It's just some background rounding that goes on in the calculation. And again, we can also see with our duct component loss factors now at 3.32, that plus 1 for F sub A is 4.32, plus 0.25 F sub H, and that's our 4.57. Now let's look at another example where we're going to change our duct diameter. Now, when we change our duct diameter, that's going to change our fittings, and it's also going to change our velocity and our velocity pressure. So what are we going to do here? We're going to change our duct diameter from 12 inches to 13 inches. When we do that, that changes our duct velocity from 4,202 feet per minute to 30,580 feet per minute. And that changes our duct velocity pressure from 1.1 to 0.8 inches of water gauge. Since SP2 is equal to the sum of our loss factors for case 2 divided by the sum of our loss factors for case 1 times VP2 over VP1 divided by the change in density factors times SP1, we now know that VP2 is 0.8, VP1 is 1.0. So let's look at our energy loss factors and see what happens with them. On our energy loss factors, we still have the same duct length, but since we've changed the diameter, the velocity has changed. So our F prime sub D changes this time, and our F sub D now changes from 1.84 to 1.69. We still have one elbow. It's a 0.19, so that remains unchanged. We have a branch entry at 30 degrees. That remains unchanged at 0.18. So now we have a F sub A of 1.0, an F sub H of 0.25, F sub D of 1.69, F sub L of 0.19, F sub N 0.18. We sum those, and that sum is 3.31. So now our sum of our loss factors for case 2 is 3.31 divided by the sum of our loss factors for case 1, 3.46, times the change in our velocity pressure, times our original static pressure, gives us an SP2 of 2.65 inches of water gauge. And again, we can see this work out on the calculation sheet. On the calculation sheet, our F sub H, 0.25. But now, since our entry loss is our F sub H times our duct velocity pressure, and our duct velocity pressure has changed, our hood entry loss has changed from 0.3 to 0.2. The same way our acceleration loss, F sub A is 1.0, but now it's 1 VP and our VP is 0.8. So now our hood static pressure loss is decreased from 1.4 to 1.0. In our duct section, again, the sum of our loss factors, 1.69 for our F sub D, plus 0.18 for our branch, plus 0.19 for our elbow, gives us a 2.06 is our duct component loss factors. That's a decrease from 2.21. And we're also going to multiply that times the lower velocity pressure, which is 0.8. So that drops our duct loss from 2.4 down to 1.6 inches of water gauge. That combined with our hood loss of 1.0 gives us our segment loss of 2.65 inches of water gauge down from 3.81. Now, let's look at another example on a system where there are two more instances where the velocity pressure method for calculating losses really come into play and make life easier. In this example, we have a screening application where we have material dropping into a horizontal screen. There's a screen going across this deck area, and as material drops into the screen, the fines drop through the screen all the way down onto conveyor belt number 1, and they're taken away in the process of conveyor belt number 1. Conveyor belt number 1 is ventilated through hood number 1. Hood number 1 forms our main duct, which runs all the way up to our dust collector, from our dust collector to our fan, and our fan to our stack. Now the overs for our screening process, that's the material that is not dropped through the screen, they are dropped down into conveyor belt 2. Conveyor belt 2 is then exhausted through hood number 2, which is ducted up and it intersects the main duct at point A. Then the screen itself is ventilated at hood number 3, and hood number 3 is ducted and it joins the main duct at point B. And then again from there, everything goes to the collector, collector to the fan, fan to the stack. What we want to look at is we want to look at what happens at this point right here where we join this branch into this main. So let's take a look. This is a calculation sheet for that example. And what I'm going to do here is let's look at hood number 1 to point A. We have a flow rate of 1,250 CFM. We've selected a duct diameter of 8 inches. That duct diameter gives us a duct velocity of 3581 feet per minute. And that duct velocity represents a duct velocity pressure of 0.74 inches of water gauge. Now, as we move through the system, we find that our F sub H for our hood is 0.25. Our hood entry loss, again, is our F sub H times our duct velocity pressure, and that becomes 0.2 inches of water gauge. Our acceleration loss is 1, F sub A is 1 VP times our VP, which is 0.74. So our hood static pressure loss is our hood entry loss, 0.2, plus our acceleration loss, and that rounds to 0.9 inches of water gauge. In our duct section, our L, length of duct, we have 20 feet of duct. We determine our F prime sub D to be 0.031. Our F sub D is our duct length times F prime sub D. And so our duct friction loss factor is 0.61. It's this guy right here. We have two 90-degree elbows. We've determined that our F sub L for our elbow is 0.19. Since we have two elbows, our elbow loss factor is a cumulative 0.38 for both elbows. So our duct component loss factors is our loss factor for our duct plus our loss factor for our two elbows. Those sum to a 0.99. That times our duct velocity pressure of 0.74 gives us a duct loss of 0.74 inches of water gauge. And that combined with our hood loss is 0.9. Again, there's some rounding in the calculations on this spreadsheet, gives us a segment static loss of minus 1.67 inches of water gauge. So now that we know that it's going to take 1.67 inches of water gauge to move this volume of air through this duct, let's look and see what happens for hood number 2 to point A. Same flow rate, 1250 CFM. Same duct diameter, 8 inches. Same duct velocity, 3581 feet per minute. Same duct velocity pressure, 0.74 inches of water gauge. We get into our duct section. We have the same hood design, so our F sub H stays the same. Our entry loss is 0.2. Since we have the same velocity pressure, our acceleration loss is the same. So our hood losses are identical on these two ducts. We get into our straight duct length, however, we only have 16 feet of duct instead of 20. So even though our F prime sub D remains unchanged, our F sub D is going to change because, again, our F sub D is our F prime sub D times our length. So our F sub D drops from a 0.61 to 0.49. Now, in this segment, we have one 90-degree elbow and we have one 45-degree elbow. And the way we calculate for that is we calculate that as 1.5 90-degree elbows. Our F sub N is 0.19. And if we have a 90 and a 45, that's 1.5 elbows times 0.19. Our elbow loss factor becomes 0.29. In this case, we have a branch entry that's 45 degree, and a branch entry at a 45 degree gives us a loss factor of 0.28. So our total duct component loss factors is our 0.28 for our branch, 0.49 for our duct, 0.29 for our 90 and 45 degree elbow. That's 1.06. 1.06 times our duct velocity pressure is 0.78 inches of water gauge. That added to our hood loss is 0.9 gives us a segment loss here of minus 1.71 inches of water gauge. Now at this point, we want to achieve a static balance between these two ducts. And we can do one of two things. We could either balance with a slide gate, or we can balance with the ACGIH balance by design using the velocity pressure calculation method. Well, balancing with a slide gate would be pretty difficult because there's not a lot of daylight between these two values. And slide gates tend to allow you to balance in larger chunks of pressure and not very small chunks of pressure. So using the balance by design method with ACGIH, we know that if we decrease the flow rate in this duct, then its static pressure will also decrease. And from an energy efficiency standpoint, that is the best route to go. However, when we look at our system information, we have a design criteria in here with a minimum duct velocity of 3,500 feet per minute. And that's the minimum velocity we need in the duct in order to keep our dust in suspension. With an 8-inch duct and 1,250 CFM, we're at 3,581 feet per minute. So that tells us we really don't want to decrease our flow rate in this duct because now we're going to drop down below our minimum duct velocity. So that tells us that we know that if we increase the flow rate in this duct, we can raise its static pressure from 1.67 to 1.71. So how do we do that? Well, we know from what's called the fan affinity laws that pressure will vary with the square of the change in volume or flow rate. And if pressure varies with the square of the change in flow, we can simply flip that around and say that flow will vary with the square root of the change in pressure. And in Chapter 9 of our ventilation manual, and also on the sidebar of the calculation sheet, we have a formula that does just that. It's our corrected flow rate is our design flow rate times the square root of the higher to lower static pressures. So if we come over here and we take 1.71 divided by 1.67, and then take the square root of that value and multiply it times 1250 CFM, that tells us that if we increase the flow rate in line 1A from 1250 CFM to 1269 CFM, that will in turn increase our velocity, it will increase our velocity pressure, and it will do so in a way that we achieve a static balance of 1.72 inches of water gauge. We've hit our target static pressure. So now we're at a position where we've achieved a static balance between the branch and the main. But we said earlier that in a branch entry, even though you have two smaller ducts combining into a larger duct, you don't always get a regain. Sometimes you get a loss. So in order to finish dealing with this branch entry, we also have to deal with what's happening to the velocity of the airstream as it moves through these two ducts into the main duct. So let's look at that. Again, now we have 1250 CFM in duct 2 to A, 1269 in duct 1 to A. We have a velocity in duct 2 to A of 3581 feet per minute, a velocity in 1 to A of 3635 feet per minute. We have a velocity pressure of 0.74 inches of water gauge in this duct. We have a velocity pressure of 0.77 inches of water gauge in this duct. And if you remember, we talked about the law of conservation of energy. We said that energy cannot be created or destroyed as it moves through a system. Well, something tells me that if we have a 0.74 VP energy here and a 0.77 VP energy here, when we combine these two airstreams, are we going to have enough velocity pressure downstream to move air through our main duct? Well, let's look at our main duct. Our main duct is duct A to B. We have a combined flow rate from these two ducts of 2519 CFM. We select 11-inch diameter duct. That gives us a 3817 feet per minute duct velocity, which we're happy with because our minimum is 3,500. But that requires a duct velocity pressure of 0.84 inches of water gauge. And intuitively, you know that combining this airstream with a 0.74, this one with a 0.77, we're probably not going to achieve a 0.84 inches of water gauge VP. And if we don't, we won't achieve this velocity. And if we don't achieve this velocity, we will not achieve this flow rate. So what do? Well, first we need to determine what is the velocity pressure resulting from combining these two airstreams. We have another formula in Chapter 9 and also in the sidebar of our calculation sheet that calculates the resultant velocity pressure of combining multiple airstreams. And we call it VPR. VPR is simply the velocity pressure of the airstream number 1 times its flow rate divided by the cumulative flow rate plus the velocity pressure in airstream number 2 times its flow rate divided by the cumulative flow rate. And when we work this out for these two ducts, we find that our VPR, which is in this line of our calc sheet, which is our weighted average velocity pressure, calculates out to 0.76 inches of water gauge. And that means that we are going to fall short of our required 0.84. So how do we address that? Well, we also know from Bernoulli's equation that velocity and static pressures are mutually convertible, which means we can convert velocity pressure to static pressure and static pressure into velocity pressure. So if we have properly accounted for all of our static losses in our system calculation, then any additional static loss we add will be converted to velocity pressure. And that's what we're going to do. So let's look at line A to B. Line A to B, our flow rate is 2519 CFM. Our duct diameter is 11 inches. Our duct velocity is 3817 feet per minute. Our duct velocity pressure is 0.84. We have 20 feet of duct. We have 190-degree elbow. We go through our calculations and we find that our duct segment loss is 0.51 inches of water gauge. So this 0.51 inches of water gauge allows for all of our losses in our main. Therefore, any additional loss that we add is going to be loss that can be converted from static to velocity pressure because it's not needed as a static loss. So that differential is 0.08. That's a difference in 0.76 and 0.84. So now we're going to add an additional static pressure loss of 0.08 to our friction loss of 0.51 and count this segment loss as 0.59 inches of water gauge. Now our cumulative, we have 1.72 upstream for our branch entries plus our 0.59. That gives us a cumulative of 2.31 inches of water gauge. And as long as we design for 2519 CFM at 2.31 inches of water gauge, within this pressure, we have enough to satisfy our static balance. We have enough to satisfy our friction losses in our main. And we have an additional 0.08, which is not required for any static losses. And therefore, again, using Bernoulli's, it's converted to 0.84 inches of velocity pressure. And now we have the velocity pressure sufficient to move the air through our system. So that's another example on how the balance by design and the velocity pressure calculation method is very easily used to balance and maintain flow rate in a system. So in summary, the ACGIH velocity pressure method for calculating frictional and dynamic static pressure losses in industrial ventilation system is consistent, it's accurate, and it's a really easy to use method for both system design and system evaluation. Any system component or duct segment have an identifiable loss factor and a known velocity pressure can be assigned a static pressure loss simply by multiplying the loss factor by its velocity pressure. The ACGIH velocity pressure method calculation spreadsheet is recommended for calculating the losses. As you've seen in the examples, it lets you see how these losses break down, and how to use that calculation sheet will be covered in a separate ACGIH webinar at a later date. Now, for additional information, see the ACGIH Industrial Ventilation Manual, specifically chapters 9, 6, 7, and 13, or any of the available industrial ventilation training courses or conferences. And those courses include the Basics in Industrial Ventilation course that you saw in the entry slides of this presentation, also the FIV, Fundamentals of Industrial Ventilation, that you also saw on the entry slides of this one, conducted by ACGIH, the AIV, Advanced Industrial Ventilation program, coming up this October by ACGIH. And then there's also the Michigan Industrial Ventilation Conference in February of each year, the North Carolina Industrial Ventilation Conference in May of each year, then the West Coast Industrial Ventilation Conference in November of each year. So there are multiple resources for additional information. And with that, Phil, that is what I have. I'm going to turn it back to you.
Thanks, sir. So at this time, if there's any questions, just go ahead, feel free to put them in the chat or in the questions section on your go-to bar, and I will get those over to Dale as soon as I can. So just as a quick reminder, you can get, or the recording is going to be up within 48 hours of the presentation. At the same time, we will be, you can download your certificate before you can do that, you have to complete the test and the satisfaction survey. And then once again, that can be accessed at learning.acgih.org. And if anybody had any issues with audio throughout it, it came in nice and clear on my side, but the magic of the internet means that sometimes something gets lost in the ether. So we'll get that recording up as soon as we can, and you can see that probably by the end of the week. So with that, Dale, I'm not sure we're getting, okay, hold on, here we go. We have one that said, I need hands-on training and I'm free to work in the Richmond area. So, just
Richmond area would be the North Carolina Industrial Ventilation Conference in May of each year.
cool.
That would be the closest to Richmond. That is in Raleigh, Durham, North Carolina.
Okay, cool, perfect. And that was
The next closest to that would be the Chicago FIV course. It's a little bit farther away, but again, not too far from Richmond to Chicago. But since the North Carolina conference is in May of next year, there is an FIV course by ACGIH coming up this October. So that's a little bit closer date for you, although it's a little bit farther away in Chicago.
perfect. So we had one, and just so that you can clarify a little bit, someone asked, so the method requires no use of instrumentation to measure any of the pressures. So is all the information used is from the system specs?
Correct.
Yep.
Now, if you're doing field evaluation, then obviously you need to use pitot tubes. What you would do is you would go through the calculation process using the calculation spreadsheet, the information in Chapter 9, and that would generate what you would expect to read in the field. And then you would take that data and go out into the field with your pitot tube or flow meters or whatever devices you have, and then you would take field measurements in order to verify how close the field measurements are to the design criteria. So when we go through the calculations on the spreadsheet and the calculations using the loss factors, those are the losses you should expect to be measured in the field.
Perfect. Okay, so that wraps everything up. Again, if there's any questions, feel free to shoot them on over. I'll get them to Dale. It's the easiest email address to remember. It's science@acgih.org. And certificates should be ready by the end of the week after you complete the survey and the test. Thank you very much for your attendance. We look forward to seeing you soon.
Yes, thank you very much also, Phil.